Alright, we're going to take a look into this class lectures, Shor's Algorithm and the Quantum Fourier Transform by Feng-Ji Lin at McGill University. So, large numbers have traditionally been believed to be difficult to factor efficiently on a classical computer. Shor's quantum algorithm gives a way to factor integers in polynomial time using a quantum computer. In addition, the algorithm also allows the computation of discrete logarithms in polynomial time. The algorithm relies in a crucial way on the quantum Fourier transform. We'll briefly introduce quantum mechanics and quantum computation, then describe both the quantum Fourier transform and Shor's algorithm in detail. So I fed the PDF into Mistral and gonna take a look what it finds. So the period finding algorithm, that's what I am interested in. The algorithm begins by creating a superposition of states using the quantum Fourier transform QFT. This allows the quantum computer to evaluate a function fx equals to a power x modulo n for many values of x simultaneously. So that is the key thing here. Thanks to quantum parallelism, this fx equals to a power x modulo n for these to x various values of x for, this can be evaluated for various values of x simultaneously. And the other thing is quantum Fourier transform, which is applied to create a superposition of all possible inputs x in the range of 0 to n minus 1. This step is efficient, so we have in this superposition represents all possible inputs of x. This step is efficient and can be done in polynomial time on a quantum computer. So the QFT is analogous to the discrete Fourier transform in classical computing but operates on quantum states, allowing for inference patterns that can reveal periodicities. Then the other thing is modular exponentiation. A power x modulo n is computed for each x in the superposition. This step is efficient due to repeated squaring, which allows exponentiation to be performed in polynomial time. The results of fx are stored in a second quantum register. And measurement and interference. After applying the QFT again to the first register, the quantum system is in a state where measurement will yield a value y with high probability if y is close to a multiple of the period r of the function f. The probability of measuring a value y that reveals the period r is significantly higher due to constructive interference of the quantum states. The measured value y is used to estimate the period r using the continued fraction algorithm. This step is classical and efficient. So this is the post-processing part. So why it's faster? The exponential speed of so general number fields saved have super polynomial but sub-exponential time complexity. That is the classical algorithm, and Shor's algorithm runs in polynomial time, specifically order of log of n per cube, which is exponentially faster for large n. Okay, and quantum parallelism allows the evaluation of the function fx for many values of x simultaneously, which is not possible in classical computing. And QFT and subsequent measurement leverage quantum interference to amplify the probability of measuring values that reveal the period r, making the algorithm efficient. And of course, we have the quantum gates such as the Hadamard gate and controlled rotation gates can be implemented efficiently on a quantum computer. The QFT itself can be implemented in order of log of n square time. So the key computation and the key saving here is order of log of n cube, Shor's algorithm. So the main thing here is this superposition of all possible input. So we are trying to find a value of r for which a power x modulo n equals to 1. The smallest value of r for which at power x modulo n equals to 1. So that's the key thing here. That's r is called the period. So in classical, a bit can be either 0 or 1. A qubit state can be represented as psi equals to alpha 0 plus beta 1, where alpha and beta are complex numbers that satisfy alpha square plus beta square. Alpha square plus beta square equals to 1. So the probabilities of measuring the qubit in state 0 or 1 are alpha square and beta square. So to create a superposition of states, quantum gates like Hadamard gate are used. So the basis states 0 and 1 into superposition. So H0 1 over root 2 0 plus 1, H1 1 over root 2 0 minus 1. Okay. So applying the Hadamard gate to a qubit which is initially in state 0 result in a superposition where the qubit now has equal probability of measured in 0 or 1. Okay, now we are interested in looking into the algorithm where the many values of x are superpositioned. So I have to ask a follow-up question here. So we have a register with 3 qubits 0 0 0. Apply Hadamard gate. Now we have 1 over root 8. Like all possible combinations are equally likely. All 8 possible 3-bit states. So this is the superposition. Now the register is in a position where all of the 8 possible combinations of 3-bit state are equally likely. So this is the superposition. Now when we are evaluating the function, we can evaluate it at all x values simultaneously. So if n equals to 15 and n equals to 2, the function fx equals to 2 power x modulo 15 is computed for x equals to 0, 1, 2 up to 7 all at once, because these are the all 8 possible 3-bit states we have. So this is the quantum parallelism, the ability to evaluate and this competition is done very super fast. So I have to ask a follow-up question. Because we have these 8 states, okay, or in a superposition way, so all of them are equally likely. But how are we having the next step parallelly? So let's delve into step 4 of Shor's algorithm. N and A, we already seen we have chosen N15, A2. So assume we have 2 quantum registers. Hold on a second. We have now 4 qubits, so we can have all 0 to 15 represented simultaneously in a superposition. And the other quantum register will store the results of fx. So initial state, both register 1 and 2. Let's say register 1 and 2 both are in a 0. The combined state is 0, 0, 0 cross 0. And now we apply some gate like Hadamard for instance, and now we have all of the 16 states in a superposition. So first register is now in a state where it represents all numbers from 16 to 0 to 15 simultaneously. So that's a symbol for this. That's an interesting symbol. Now x. So now when we are applying this fx operation 2 to the power x modulo 15 as a quantum operation onto that superpositioned input, and we get the result in the second register. So we'll have for f01, and we have this for each x in the superposition, fx is computed and stored in the second register. So f0 we have we'll store 1, f1 we'll store 2, f2 will store 4, f3 will store 8, f4 will store 1. Here we can see the periodicity starting, so possibly r equals to 4, that's the period. And so the quantum computer evaluates fx for all x values simultaneously due to superposition. And this is the essence of parallelism. Instead of computing fx one by one as in classical computing, the quantum computer processes all these computations at once. So apply the QFT to the first register. This transforms the state in a way that upon measurement it will yield values that help determine the period R. So we apply the QFT now in the first register. So we have the fx values now in the second register, and the x values now in the first register. So now I need to do another follow-up question. Great example. So we are looking at it on a step-by-step basis. So after evaluating fx, the quantum state is 1 over root of 16 x goes to 0 to 15 x cross fx. For instance, f0 is 1, f1 is 2, f2 is 4, f3 is 8, f4 is 1, and such and such. Now the QFT is applied to the first register, transforming the state into the frequency domain. So we have now y equals to 0 up to 15, a to the power twice pi I xy divided by 16. That's where the period comes into play. Period works with frequency, right? So this transformation creates interference patterns that will help reveal the period R. So now the measurement results are concentrated around multiples of the period R. So notice that R is a value that is actually in the domain for x equals to 0 to 15, 1 to 15. So it's what the transformation does is that the probability of measuring a particular value y changes influenced because of the periodicity of fx. So this is what we are gonna look into. So I have asked this another follow-up question. Remember that all the time we have that book and in the attachment. So this is the concrete example. So we saw that the period is 4, r equals to 4. So after creating a superposition, notice before creating the superposition, all of the 16 states are equally likely. So all 16 of them, all 16 possible values of x had equal amplitudes, you can say, in the frequency domain. So, but after applying the QFT, the amplitudes for y values that are multiple of 4 interfere constructively. So amplitude of y function of x equals to function of x plus 4 and so on. So more likely to observe values like 0, 4, 8 or 12 because the amplitudes have been reinforced through constructive interference. So this will reveal the um, period, and eventually you will find out that r equals to 4.